Hello students, welcome to ePhysics. Students, in this video we will be discussing about the solid exercise questions of Ncert of chapter Wave Optics. So, here is the first question. Students, the question is, monochromatic light having a wavelength 589 nanometer from the air is incident on a water surface. Here, the first thing given in the question is lambda, that is the wavelength, is equals to 589 nanometer, which can be written as 589 multiplied by 10 to the power minus 9 meter. Nano means 10 to the power minus 9. Students, the first thing that we have to find the frequency, wavelength and speed of the first part of the question of the reflected wave or the reflected light. Here, for reflection, students, we know when the light reflects, it incidents from one medium and reflects back on the same medium. Therefore, in this, the reflected wave will have same wavelength, same frequency and same velocity of the light as it was having for the incident wave. Clear? Now, here, if we are supposed to find the frequency of it, then how will we find the frequency? Now, we know a formula that C is equals to nu multiplied by lambda, where this nu is equals to frequency. Okay? Now, frequency will be equal to C upon lambda, where C is the speed of light in vacuum. So, this can be solved as nu is equals to the value of C. We all know that it is 3 into 10 to the power 8 meter per second divided by lambda. It is already given that 5, here it is already given 589 into 10 to the power minus 9, and the unit of frequency is hertz, so we have to write hertz over here. So after solving it, we get the answer, that is 5.09 into 10 to the power 14 hertz. Clear? Now, the second question says find it for the refractive light. Okay, for the refracted light, let us first erase it. You can take the screenshot if you want to take it. This is the first part of the question. Now, after erasing, let's erase it. Now, the second part of the question says, the second part, find the frequency, wavelength and speed for the refracted light. Okay, now students, the frequency of light, that is the nu, frequency of light never depends upon the property of the medium. Okay, never depends upon property of the medium. Okay, property of the medium. So it means the frequency of the incident wave will be equal to the frequency of the refracted wave or the refracted light. Here students, we have been given the refractive index of water, and by formula we know that refractive index is equals to C upon V. Yes, C is the velocity of light in vacuum and V is the velocity of light in any medium. So here, velocity of light in any medium, here we have taken water, so we will write it as, let us consider VW, which can be written as the velocity of light in air, that is C, divided by nu, that is the refractive index. Here, velocity of light in water is equals to 3 multiplied by 10 to the power 8 divided by 1.33. Final answer after doing the calculation, we get it is equals to 2.26 multiplied by 10 to the power 8 meter per second. Clear? Now students, if we are supposed to find the wavelength, Students, we know this from this formula. Wavelength, in the previous one, we have studied in the first question that C is equals to nu multiplied by lambda, which can be written as, if we are supposed to find the lambda, can be written as C upon nu. Where here we have taken the speed of light in vacuum, but here we will be taking the speed of light in water. Okay, speed of light in water divided by nu, the frequency that we have found in the first part of the question. So it is equals to 2.26 multiplied by 10 to the power 8 divided by frequency. In the first part we have found it is equals to 5.09 into 10 to the power 14, and frequency's unit is hertz. After solving it, we get it is equals to 444.0 into 10 to the power minus 9 meter, or you can also write it as 444.0 nanometer. Okay, nanometer, you can write it. So that's it with the first question. Okay, now let's move to the second question. Here, the question says, what is the shape of wavefront in each of the following cases? In the first case, the light diverging from a point source. Students, we know if we have a point source, the light will diverge in all the directions. Okay, in all the directions, and the wavefront so formed will be spherical in shape. So in the first case, it will be spherical. Okay, now in the second question, second part, the light is emerging out of a convex lens when the point source is placed at its focus. Suppose, students, we have a convex lens and this is one of the focus of this lens. Okay, let us consider we have the point source over here. We know when the light ray incident on the lens from the focus, it moves parallel to the principal axis. Okay, now the wavefront so formed will be parallel. Okay, so we get finally parallel wavefronts. Clear? Now students, in the third part of the question, it says the portion of the wavefront of the light from a distant star means the object is kept at infinity. Now from there, if we see the light rays incident on earth, we have to consider any portion of this, and that portion is considered to be as plane wavefront. Plane wavefront. Yeah? So that's it with the second question. Now we'll move to the third question. Students, here the refractive index of glass is equals to 1.5. So the first part says refractive index is equals to 1.5, and the speed of the, what is the speed of the light in glass? So we have to find the speed of the light in glass, and we know the speed of light in vacuum is equals to 3 into 10 to the power, sorry, it is mistakenly written 10 to the 108, but it is nothing other than 10 to the power 8 meter per second. Clear? Students, we know the formula that refractive index is equals to C upon V, where V is the speed of light in the glass and C is the speed of light in vacuum, and nu is the refractive index of the glass. So V can be written as C upon nu. Here V is equals to C, the value is 3 into 10 to the power 8 divided by nu, it is equals to 1.5. Velocity's unit is meter per second. So finally we get the velocity 2 multiplied by 10 to the power 8 meter per second. This is the velocity of light in the second medium. Student, the second part of the question says, is the speed of light in glass independent of the light, of the color of the light? If not, which of the two colors, red and violet, travel slower in the glass prism? Students, we know we have studied the phenomena of dispersion in prism. When the white rays incident on the prism, it gets dispersed into 7 different colors. and the deviation, most deviation is of the violet component of the white light, and the least deviation happens for the red colored component of the white light. From here, students, we can conclude that from here the refractive index of violet light is greater than the refractive index of red light. Therefore, the velocity of violet is less than velocity of red. Okay, so here the second part of the question says, which of the two color, red or violet, travels slower in the prism? So the violet color will travel slower in the prism. And is the speed of light in the glass independent of the color of light? So no, it is not independent. We have seen over here that the speed of the light in the glass is dependent on the color of the light, because here we have red color, here we have violet color. The velocity of violet color is less and the velocity of red color is more. Okay, so that's it with this question. Let's move to the next question. Students, here we have, in Young's double slit experiment, the slit are separated by 0.28 millimeters. That is, the value of d, small d, is equals to 0.28 millimeter. Students, we need to convert it into meter because the unit of the length is meter. So we can write it as 0.28 into 10 to the power minus 3 meter. Clear? And the screen is placed at a distance of 1.4 meter away. So capital D is equals to 1.4 meter. This distance is already in meters, so we need to convert it. And 1.2 centimeter is the distance between the central fringe and the fourth bright fringe. Fourth bright fringe means the value of n is equals to 4, and the distance here, students, when the slit from the slits, the light source comes, it incidents on the y-axis. So let us consider y is equals to 1.2 centimeter. Here it is in centimeter. Again convert it into meter. So it can be written as 1.2 multiplied by 10 to the power minus 2 meters. Clear? Now, for constructive wavelength, we have to, here we have to determine the wavelength of the light used in the experiment. So wavelength, students, we know the formula for constructive fringe. Okay, for constructive interference. Okay, interference, we know the formula y is equals to n lambda capital D by small d. Here lambda can be written as y multiplied by small d divided by n multiplied by capital D. Okay, which can be written as the value of y is equals to 1.2 into 10 to the power minus 2, and the value of small d is 0.28 multiplied by 10 to the power minus 3 divided by the value of n is 4, because here it is forming the fourth bright fringe, that is 4 multiplied by capital D, which is equals to 1.4 meter. Clear? From here, students, when we calculated, we get the value, that is lambda is equals to 6 multiplied by 10 to the power minus 7 meter. Okay, 10 to the power minus 7 meter, or it can also be written as 600 multiplied by 10 to the power minus 9 meter, or it can also be written as 600 10 to the power 9, 10 to the power minus 9 means nanometer. Clear? That's it with this question. So here, students, in this question it is saying that in Young's double slit experiment, using the monochromatic light of wavelength, the intensity of the light is given. Okay, now students, let us consider the amplitude of the first wave is A1 and the amplitude of the second wave is A2. Now students, remember one thing, intensity is always equals to square of amplitude. Okay, now the resultant amplitude of the two waves will be equal to A square equals to A1 square plus a2 का square plus 2a1 multiplied by a2 cos phi, where phi is nothing other than the phase difference. Phase difference. Clear? Now, students, this a square can be replaced as I is equals to I1 plus I2 plus here a is equals to root under I. So we can write it as 2 multiplied by root under I1 multiplied by I2 cos phi. Clear? Students, we know this is a monochromatic light, and for monochromatic light, students, okay, we know that I1 will be equal to I2. Therefore, the resultant intensity will be equal to I1 plus of I1 plus of 2 root under I1 multiplied by I1 cos phi, which can be written as I is equals to this I1 plus I1 becomes twice of I1, and here it becomes plus 2 I1, because I1 multiplied by I1 is I square and root under I square is equals to I1, and finally we have cos phi. Let us consider this is nothing other than equation 1. Here we have been knowing a formula that phase difference is equals to 2 pi by lambda multiplied by path difference. Okay, path difference. You must have studied this formula in class 11th. Okay, now here phase difference phi is equals to 2 pi by lambda multiplied by the path difference. In the first path of the question is, it is given that is in path difference is k units. Okay, now let us take it is lambda. In the Young's double slit experiment using monochromatic light wavelength, it is not given here, so let us consider this is nothing other than lambda. So this is lambda and lambda gets cancelled, so we are left with phi is equals to 2 pi. Clear? So we have got the phase difference, that is phi is equals to 2 pi. And here in this question formula equation 1, we have cos phi, students, and cos 2 pi is equals to 1. Clear? So let's put this in equation 1. So we have here that I is equals to, it becomes twice of I1 plus twice of I1 multiplied by 1, which can be written as 4 times I1. So finally we have this one, and here students, here it is written the intensity of light at point where the path difference is, we have to find it is path difference is k units. It is given k units. So here intensity is given, okay? It is already given in the question that I is equals to k, and we have found I is equals to 4 I1, so it can be written as 4 I1 equals to k. Therefore I1 is equals to k upon 4. So this is for the first one. Now here students, the question is not written over here, so we have to find what is the intensity of light at a point where the path difference is, let us consider lambda by 3. Okay, it is there in the Ncert exercise, it is lambda by 3. So from here phase difference, that is equals to phase difference, that is phi equals to 2 pi by lambda multiplied by lambda by 3. Lambda and lambda gets cancelled, so we are left with 2 pi by 3. So here this is 360 by 3, which is equals to 120, which can be written as cos 120, which can be written as cos 90 plus 30, which can be written as minus of sine 30, which can be written as minus of sine 30's value is minus 1 by 2. So, from here we can write from this equation, okay, in place of cos phi here it was equals to 1, and here we have to put minus of 1 by 2. So, I is equals to 2i1 plus 2i1 multiplied by minus 1 by 2. This 2 and 2 gets cancelled, so we are left with 2i1 minus of i1. So finally we have i1. So here also I is equals to i1, which is equals to i1 is equals to k by 4. So we have done with the second part of the question as well. Let's move to the next question here. Students, here we have been given that the beam of light consisting of two wavelengths, let us consider lambda 1 is equals to 650 nanometer and lambda 2 equals to 520 nanometers, is used to obtain interference fringes in Young's double slit experiment. Then find the distance of third bright fringe. In part A, it is n equals to 3, okay, from the central maxima for wavelength 650. That is, we will be solving for question first wavelength, okay. Here, students, we have studied that for constructive wavelength, constructive interference, it is equals to y equals to n lambda capital D by small d. Here the value of capital D and small d are not given, so we will not be putting it. So here n is nothing other than 3 multiplied by lambda, which is equals to 650 nanometer, multiplied by capital D by small d nanometers. So after solving it, we get y is equals to 3 multiplied by 650 is equals to 1950 capital D by small d nanometers. Here the value of capital D and small d are not given, so we are not going to put it, but we have found what we were supposed to find, okay. The length of the distance of the third bright fringe on the screen from the central maximum, we have found it, okay. Now let's move to the second part, that is B. What is the least distance from the central maximum where the bright fringes due to both wavelengths are coinciding? If they are coinciding, let us consider the wavelength 2 is forming at nth, okay, at forming the nth bright fringe, and wavelength 1 light is forming the n minus 1th bright fringe, okay. If they are coinciding, then we can write n lambda 2 will be equal to n minus 1 lambda 1. If they are coinciding, it means both are at a single point. So here we can write it as n lambda 2. Lambda 2's value is 520, so it becomes 520 equals to lambda 1 into n. Lambda 1 into n, lambda 1 is equals to 650 multiplied by n minus lambda 1 into 1, that is equals to 650. This becomes 520n minus of 650n, which can be written as equals to minus of 650. Here it is equals to minus 130n. Minus 130n equals to minus 650. This minus and minus gets cancelled. Therefore, n is equals to 650 divided by 130. Therefore, n is equals to 5. Now, putting the value of n in that for constructive fringe equation, that is y is equals to n lambda capital D by small d, we could find it over here that n is equals to 5. Lambda ka value we have to put it for the second wavelength, that is 520 multiplied by capital D by small d. Here also again the value of capital D and small d is not given, so we will leave it as it is. So finally we get to the conclusion, it is equals to 2600 multiplied by capital D by small d Newton meters. So that's it with the video. Thank you very much for watching.